introduction. We simply thank him for having accepted to give this talk at such short notice. And he will talk on knots and links coming from the Thompson's group.
Okay, so I apologize to the operator algebra people for imposing yet another talk in an already busy week of talks, but I couldn't resist this opportunity to come and talk about this stuff because for me it's all part of the same program as what I talked about on Monday in this Thompson group representations and so on, but it sort of splits into different parts, and this particular part that I really want to talk about today, the beginning, is a little bit buried in a paper called No Go about looks like it's about quantum mechanics, but it contains this stuff which is pure algebra about groups. So there's been a lot of talk of Thompson groups and maybe even a few definitions. So I just want to quickly go over the Thompson group definitions. I'm mostly going to be working with F today, but T will be around and V is even further, more peripheral. But this is the traditional name for it, F, which is a little unfortunate because it has certain relations with the free group. And there's Thompson groups F sub n for every n. So there's some confusion. So what I'm going to do is, if ever I have to talk about the free group Fn, this will be the free group. So what is F? Well, as a set, it's a set of all homeomorphisms of the unit interval. Let's say little f. F of 0 is 0. And then there's a bunch of properties. First of all, it's piecewise linear with only finitely many discontinuities or singularities. Let's call them bad points. That's where the derivative doesn't exist. And the bad points are dyadic rationals. And the slopes, when they exist, which is most of the time, are all powers of 2. All right. So just in case you've never seen these groups before, there's probably some people who haven't, let me just point out a few things about them. First of all, if you want to give one, you can always do it by its graph. Right, this is 0, 1. This is 0, 1. And here would be a nice Thompson group element. We could send a quarter, between 0 and a quarter, we could give it a slope of 2. So this would get us up to 1/2. Between 1/2 and 3/4, we could give it a slope of 1 exactly, which would get us over here. And then between 1/2 and 1, we give it a slope of 1/2. It says there's the graph of a function which is manifestly in the Thompson group. Okay. The trouble with this, drawing the graphs, is, when they get a bit more complicated, the graphs all kind of look alike, and you don't really see that much from drawing the graph. If you're even a little bit sloppy about where you put the points, then you can't tell one element from another. So one of the things we're going to do is, first thing really, is get a nice notation for elements of the Thompson group. Questions about the Thompson group that as I said, if you haven't seen it before, you may ask yourself. It's countable, right? Countably many dyadics and countably many slopes. Is it simple? No, it's not simple, because in fact, if you look at the endpoints in the neighborhood of 0 and 1, there's a well-defined slope there, and if you take the logarithm base 2 of that slope, at either endpoints, you get a group homomorphism. So in fact, the Thompson group surjects onto Z plus Z, but in fact that is an exact sequence, right, from F. Right. So it has this structure, but it turns out this guy is simple. Okay, the commutator subgroup is simple. So it's a nice example of an infinite. It's infinite because it's obviously torsion free. Simple group. All right. Any other questions? Oh yes, of course the famous question which comes up every time anyone defines it is it amenable or not? And I don't know. I don't see any particular reason why the tools that I'm going to develop shouldn't, in the long run, lead to the answer that question. But it's clearly, from the numerical evidence, it's a very difficult question to answer. All right. Now, what I want to do is, as I said, get this very concrete combinatorial description of it. And we're going to start with the tree of standard dyadic intervals. So we're going to get that by taking the unit interval and then splitting it into 1/2. And so on. So all we do is we take an interval and split it in the middle and keep on going. So by definition, a standard dyadic interval is one that arises on this tree. And the relevance to the Thompson group is that there is a fairly simple lemma, which is the proof of which is just keep subdividing until it works. If given f belonging to f, there exists a I1, I2 up to ik, a standard dyadic partition and by that, of course, I simply mean a partition of the interval into standard dyadic intervals, so it's going to have something to do with this tree. With the properties, with some important properties, the first one is that f is linear, or affine, I guess, affine on each I sub j. So once you're in one of these intervals, it's just a slope. There's no bad points inside that interval. And also, this interval f via j is a dyadic partition. Standard dyadic partition. Right, so as I said, this is it's not completely trivial, it's almost trivial. The hard thing, of course, is to get the second part, but you just keep subdividing until it works. And but it has great importance for us because it allows us to talk about everything in terms of this tree. So let's think about what it means to have a standard dyadic partition in terms of this tree. Well, if you think about it, let's just take one, and I'll tell you. So this is going to be a proof by example. So let's draw a subtree of this tree, which I'll put in blue. Right? That consists of this interval, and this interval. Okay? So these intervals are manifestly a dyadic, standard dyadic partition. Okay, just look at it, that's the way it has to be. So we see immediately by this example that standard dyadic partitions and subtrees of this tree is one and the same thing. Okay? So this is the same thing, a subtree of the tree of standard dyadic partitions. Okay, so now what this means is that we've got this lemma saying that Thompson group element takes one standard, there is a standard dyadic partition that takes it to another. So in translation to the trees, there's a tree such that it takes the one tree to the other. It takes the leaves of this tree, you'll notice, are the intervals of the standard dyadic partition. And this says that there's a given any element of the Thompson group, there's one of these trees, and the Thompson group sends the leaves of one tree to the leaves of the other in the only way possible, because it's not allowed to split, it's not allowed to have any bad points, so it's just got to be affine on the interval. And conversely, if you have two trees with the same number of leaves, then you can just start on the left and send the left interval of the first tree to the left interval of the second tree by some scaling, and then the second one you do the same, and so on, it all matches up, and at the end you have a Thompson group element. Okay, so there's a natural correspondence between Thompson group elements and trees. So let's do an example. Let's take the tree that we gave, which is this one. It has 3 leaves. Well, there's not too many trees, other trees to choose from that have 3 leaves, so let's choose the only one that's going to give us any juice, which is that one. All right, so what I'm saying is that this pair of trees defines an element of the Thompson group. How? Well, what's this interval? This is the interval 0 1/4. This is the interval 1/4 or half. And this is the interval 1/2 1 on the top. What about the bottom? This is the interval 0 1/2. Right, reading up from the bottom. Sorry, I put it upside down. That's because I'm jumping ahead of myself. So, that's, I guess at this stage, strictly speaking, there's no reason why it shouldn't be the other way around. But so this one is, what's, someone tell me what this interval is from the bottom tree. 1/2 3/4, fantastic. And finally 3/4 1. So the Thompson group element simply does this with a slope of 2, this with a slope of 1, and this with a slope of 1/2. It's the same as this guy here. Okay. So that's the Thompson group, and clearly this is a nice way of combinatorial way of representing the Thompson group elements. In fact, you could make it completely combinatorial as soon as you've solved the uniqueness problem. So I said that to any Thompson group elements there's a pair of trees. How unique is it? Well, I mean, for instance, if we had put this one upside down and used the same one on the bottom, then what would this be? This would be the identity, right? Because this is just sending the 0 1/4 to 0 1/4, 1/4, okay? So the idea is that these things are called carrots. And if you ever see a carrot on the bottom, carrot on the top, meeting each other like this, then they just sort of cancel, and because of this, and so you can cancel carrots, and then you get this tree, and that's a carrot, and you'll be down back to the identity. So there we go. Anyway, the theorem is not very hard. That if you take trees, pairs of trees, modulo cancelling carrots, then that is exactly the same as the Thompson group. That's the only non-uniqueness. And you know, if you do cancel carrots in any 2 different ways, you always end up with the same thing. And there's none left to cancel. Okay, so is everyone happy with that?
What's the composition?
What's the composition? Well, that's a good point. Actually, I have sort of 2 answers, both of which I want to give in the talk. Yeah, okay, let's do it now, quickly. So it doesn't require much thought to see that if you have, let's just draw them as T1 on the bottom and T2 on the top, and then T3 and T4. Okay, I'm thinking of the mappings as going that way, am I? No, I'm thinking of them as going I guess I decided that that was there to make those the same. So I was thinking this is going this way. I may change. But anyway, it doesn't require much thought to see that if T1 is actually equal to T4, then the answer for the composition is T2, T3. It's simply because between T1 and T4 you don't do anything if they're the same. So that allows us to solve the problem because you can always stabilize by adding carets. Okay, do this operation backwards. So you take T1, T2, T4 and T3 and then you stabilize T1 and T4 so they look the same. You may be able to do this economically, but you can always do it by stabilizing to the point where they're just the whole full tree, you know. Okay, so that's the composition trees. So, you know, you could write a computer program for that without any trouble. There's another way to do it, which is much better for hand things, which I'll hopefully come to at the end. All right. Any more questions on this? This way of representing Thompson group elements. Okay, good. So now I want to go on and basically do this again. I'm going to do this same definition again in a slightly different way. So almost imperceptibly different way. But I'm going to make it look very different right at the start. So what I'm going to do now is I'm going to do a very general construction that works often for groups, to construct groups, and by applying it to a certain situation we'll get the Thompson group. So this construction is basically due to, I guess, a Norwegian called Ura. Is that how, I don't know how you say that. They made us say Ula for Bradley, so presumably it's Ura for this guy. Anyway, he had a way of getting, if you have a semigroup with a bunch of properties, you can get a group of fractions. Not commutative, there's a bit more guts to it than that. But I'm going to do the same construction, except I'm just going to doctor it up a little bit and have a category rather than a semigroup. So here's the setup. I'm going to start with the category C. By the way, those of you who know me know that I have a very much love-hate relationship with categories, and I don't use the word unless I really have to, but it's definitely the right thing here. C, and it's going to have three properties. It's going to have an element which I'm going to call 1 because it's 1, that's what it looks like in C, and this has the property that, first property is that the morphisms from 1 to C is not empty for all C belong to the object. So this is not much of a property, but given that I'm going to call T, some kind of curly T, the set of all pairs, the disjoint union of the C of the morphisms from 1 to C. I guess it's probably already disjoint, maybe, I don't know. So that's what T is, and the other two properties are going to involve the set T. And the first one is, they've got names, which is stabilization, which is for all T, S, and T in this curly T, there exists E and F in the category, such that ES equals FT. So I'm suppressing the composition in the category, so there'll be E circle S equals F circle T. Okay, so if I have a pair, then I can find another pair that stabilize them up to make them the same. That should start to sound familiar. And the third one is cancellation. And that says if I have S and T belong to T, and CS equals CT, then no, sorry, that's not right. If I have T belonging to T and CT equals DT, then C equals D. So C and D are in the category, T is in this part of the category. Alright, so this is all junk, you know, how are you supposed to relate to this? Well, let me do the example we're after and see what's going on. I should say that there's lots of examples of this cropping up in categories, and I have by no means investigated them all. I've just been focused on this Thompson group and how it relates to this stuff. So for the Thompson group, we're going to let C equal the category of planar rooted forests, binary planar rooted forests. So the objects are the numbers, and the morphisms are binary planar rooted forests with so I'll draw a picture and then it'll be obvious. Okay, so this is a binary planar rooted forest because these are real points here, and it's planar, so there's no ambiguities about which comes before which. And it's a morphism from 1, 2, 3, 4 to 1, 2, 3, 4, 5, 6, 7, 8. Obviously, concatenation in the category is just stack one on top of the other. Okay? Well, a 10 seconds thought. Well, you'll convince yourself that, that this has all of these properties. So the initial object is just this one. So there it is. It's a tree. It's also a binary planar rooted forest. And stabilization is that thing that I said before. In order to do the composition, remember, we had to stabilize two things to make them the same. Then you could do the composition. And cancellation is sort of obvious. If you have a tree like this, and then you stack two forests on top of it, and you get the same thing, and you just cut the bottom away and you'll see the forests. So it has this cancellation property as well. Okay? So that's the example. I mean, you could think of simpler examples. You could think of the natural numbers as a category with one object, and either addition or multiplication as a category structure.
Could you say stabilization again? Sorry.
Did I get it wrong?
I don't know. I didn't catch it. For the tree for the binary planar rooted forest.
Oh, for the binary planar rooted tree, why is it stabilization? Well, if you have any tree, right, then you just start subdividing the things, and eventually you're going to get, if you want to, you can get to the whole tree, right? So you get all of these intervals.
All right. Yeah. Okay. Yeah.
Okay.
Thank you. Yeah.
You might be able to stabilize them a lot quicker, but you can certainly do it that way. All right. So lots of categories. Here's another one that is a bit more interesting, perhaps. If you take the braid group, you can take just positive braids. You can just take positive braids and think of that as a category with one object, and the braids as the semigroup of positive braids as morphisms. Well, and you can enjoy thinking of lots of other examples. But the point is that this theorem, which is basically OR, and it's really not very hard, is that given C with these properties, we can consider, let's call it G sub C if we have to, as the set of all Cartesian pairs, two elements of T. Remember, T has these morphisms from one to everything, and that's the same in the Thompson group picture, and why I called it T is this is trees, right? Binary planar rooted trees. So it's pairs, which I'm going to suggestively write T1 over T2. That's it. T1, T2 belong to T, and the image, the target, of T1 equals the target of T2. Right. So modulo the stabilization, so ST1 over ST2, the equivalence relation generated by this, right? So this is cancelling. So remember, this in a more mundane notation would just be the set of all ordered pairs T1 and T2, but for obvious reasons I'm running at T1 over T2. Then I claim that the claim is that this is a group with the group operation T, let's do it this way, S over T times T over P equivalent TU equals S over U. Okay, and that suffices. Why does it suffice? Well, you know, if this, in order to have it, I have to have this T being equal to this T, but we already went through that with the things. By stabilization, you can always arrange that. So the work is simply to show that it's well defined, and inverses, well, that's not hard. Identity is obvious, and so on, and it's associative. So those are all trivial, just a little bit of work. Anyway, so this is the group of fractions of the category. All right. With all that I've said so far, no one in this room will have any trouble figuring out what the group of fractions is for the category of rooted binary planar forests, will they? If you do, then you shouldn't be here. It's the bloody Thompson group, isn't it? So anyway, so obviously from what I've said, if you apply this to this category of forests, then you get the Thompson group as the group of fractions, sort of by definition. And I even did the composition for you, and we saw it's the same composition. If you had the natural numbers with addition and the zero, what would you get? You would get the integers. If you had the natural numbers with multiplication, you would get the positive rationals. If you had the positive braids, you'd get the braid group, and so on. Okay. All right, you'll all be thinking to yourselves, is this it? You know, surely this is not the story. Well, it is the story, and I should say that for those of you at my talk on Monday, there was a lot of, I talked about representations of Thompson groups coming from these quantum spin chains, and I hinted at how you could define them by local scale transformations, and I also said out loud that it was a real pain if you try to do it that way. Well, it is a real pain, and this turns out to be the elegant way to do it. I was sort of given a little bit of a nudge in this direction by Dylan Thurston. Right, so what? So I've given a construction which is barely different from the usual construction of Thompson. I've seen that it applies in lots of other situations. What does it buy me? Okay, so here's what it buys me. What I claim is that every time I have a functor, you know, I have to use this categorical word, a functor from C to any other category, maybe it's got to be small, but all categories are small for me anyway, to any other category, as soon as I've got a functor, I get an action of the Thompson group on something. Okay? And it works in this general context. So every time I have a functor from this category to any other category, I get an action of the group of fractions on something. Okay, so what's that something? That's what I'm going to explain. So you see, one of the things I didn't say about Thompson maybe I should have said was, it's not a super user-friendly group. See, it's not sort of like the braid group, and because this commutator subgroup is simple, then you're never going to be able to write down any finite dimensional representations which contain anything but the abelianization. Okay, this is a Tits alternative or some such thing. So, you know, unlike the braid group where you can write down this Yang-Baxter matrices or whatever and play with them and have a lot of fun and compute like crazy, with this one, no finite dimensional representations. So when I construct these representations, they are necessarily going to be on infinite dimensional vector spaces if they're linear. And I'm sorry, I'd love to have some finite dimensional ones, but no joy. All right, so here we go. So let's do this. So this is the main construction that's coming now. As I said, it's very elegant, in my opinion, but it totally and completely obscures the original intuition of the Thompson group as being these homeomorphisms. So let's, just one thing to set up, which is we're going to put a structure on T. So once again, I'm in the context of one of these categories with these three properties, and I claim that T becomes a directed set. S is less than or equal to T if and only if T equals CS. The C is in the category. Okay, so if you think about this in terms of trees, it just means that you've subdivided. Because S, these C's are the forest, and they tell you how to split further. So this is just saying that, okay? So this is a directed set. It follows immediately from the axioms. Okay, and now, given a functor phi from C to any other category K, a functor, then I'm going to use it to define a direct system. So the words a directed set, direct system, no ED, and I have that on the authority of Wikipedia. So, this is the directed set, and the direct system. I'm going to take. What do you have to do for a direct system? You have to take every element in your directed set, send it to some set, and every time you have an S less than or equal to T, you've got to define some sort of connecting map. I forget what the right word is for that. So what we're going to do is we're just going to follow our nose. We're going to give T belonging to T. Use phi. So phi, we've got to get a set. So we take the target of T, we take phi of that. Simple. All right, now the connecting maps, we just follow our nose. Suppose we had S less than or equal to T. Then this would be going to phi of the target of S. And I guess in the very first lecture on category theory, you would know that the functor means that there's phi of what do we call S? C. Going from the target of S to the target of T. Okay, so you can check it's well defined. That follows from cancellation, blah, blah, blah. It's a direct system. And when you have a direct system, you have a direct limit. And that's what the group of fractions is going to act on. Right, so it's this. So the theorem here, I'll put it in red, is that given one of these phi's, let's give it another name. I think I'm going to call it A sub T, just to get rid of some letters. So A sub T is the thing given by the functor according to the image of T. So the theorem is that G sub C acts on the limit of A T by the formula. Well, we're going to take this. What is the direct limit? The direct limit is a set of ordered pairs, right? An element of T and an element in its image. And you identify them if they get identified under this process. That's also in Wikipedia. So by definition, an element of this limit of A is going to be a pair given by T and an X, where X is in phi of the target of T. All right, so the formula is this group of quotients acts on the limit by the following formula: S over T times T over X equals S over X. Okay? Same formula. Same proof. Okay, so the fact that this is an action and everything's well defined is exactly the same as in the proof of Orr's quotient theorem. Fantastic. All right. So what I want to do now is spend the rest of the lecture giving you 5 different examples of how this can work in the Thompson group. You'll see that you get some kind of diversity of possible applications, one of which is to knot theory. Okay, but just before doing that, maybe I should, before narrowing down on the Thompson group, should just say how it works in the braid group. Okay, this might be of interest to some of you. Because there's sort of something hidden here. I said the group acts on something. Group acts on. So we have a semi-group action, and that gives you a group action. So in the braid group, if you're ever thinking about braids, and you end up getting some sigma i's such that the braid group relations are satisfied, then you're happy, right? That's the hard part, the hard thing to do. But unfortunately, the damn things are not invertible. They have kernels, so you don't get a representation. Well, fear not. This theorem says you get an action of the honest representation of the braid group, okay, on some space. So even in something more familiar, there's some consequences of this. Well, let me get on with the Thompson group, and I'll tell you how this works, how this gives you some interesting actions and representations of the Thompson group. I never said what T was or V was, did I? Well, T is just F on the circle instead of being on the interval. And V is where you allow, they're not necessarily homeomorphisms, you allow interval exchanges as well. In fact, this tree, this forest picture works for those two as well. Right, so we want to get a functor from the category to some other to some other category. The category was this category of trees. Well, this category of trees doesn't really have much in it, does it? It just has this guy, and then maybe putting things like that. So all you really need to get a representation of, a functor from this category to another one is you have to know what to do with this fork. And you just have to know that when you slot it in the right places that it works. And the only thing, in fact, is this, all of the TQFT people know this from square one, that this equals. So as soon as you can represent these, a fork and this obvious homotopy thing, then you've got a functor, and therefore an action of the Thompson group on something. Okay? So now we just let our minds roam free, and you'll be amazed, I haven't even started to exhaust the possibilities here, how many times you get the fork. So let's start with a really simple one, which I kind of like. We've got a bit late in the game, and that will be where the category K has objects, the interval 0 to n, and the morphisms are diffeomorphisms, which are, let me be tough on them and make them to equal the identity, well, let's say linear slope 1 in a neighborhood of 0 and n. Okay, so for instance, if we had a morphism from the unit interval to the interval from 1 to 2, from 0 to 2, it could be given by a graph. Point is, it's got to have this slope here, and to all orders. That's the main thing. And then at 2, it's also going to have that slope there to all orders, slope 1. In between, it can do anything it likes as long as it's a diffeomorphism. So that's a morphism in the category. And not only that, but this is a morphism which goes from the unit interval to the interval from 0 to 2. So therefore it determines an action of the Thompson group on the direct limit space. Churn away, this is actually a surjection. So therefore the direct limit is easy to calculate, it's just the unit interval itself. So we get the Thompson group acting by smooth diffeomorphisms on the unit interval. So every time we have one of these, action of F on 0, 1, smooth. Okay, so we've managed to make all of those discontinuities in the Thompson group go away, and we've got an action by smooth diffeomorphisms of the interval. So I don't think it's a conjugacy. So Gis and Sergescu actually showed that Thompson group is actually conjugate to a subgroup of diff. So this shows it's very easy to actually smooth them. Right, so that's one. Here's another one. So group people might like. So all we've got to do is represent the fork. So I'm going to do another one with a category K. The category K, the target category, the object of it is going to be the free groups, object Fn. Okay, and for the morphisms, I've got to represent the fork. So what's the fork? That's going to be from F1 to F2. When I get a homomorphism from F1 to F2, it's just an element of F2. Right, so I'm going to take, the morphisms are homomorphism, group homomorphism. So the fork, choose W belonging to F2. So this is a word on X1 up to, this is a word on X1 and X2, say. And then in order to represent this, let me try and do it. I'll probably get it all wrong, but you can fill it in easily and get the correct things. I would send X1 would go to X1, X2, this would be Xi minus 1. Then Xi here would go to W of Xi plus 1. And after that, Xi plus 1 would go to Xi plus 2. And so on. So it's trivial to check that that satisfies, that gives you a functor. So we get an action, therefore, by automorphisms, because Thompson group action is going to preserve the structure in the target category, like we got smooth from there. Action by automorphisms on this direct limit group. F acts on some limit of the Fn's. Okay, so you might ask, well, what is that limit? Well, that's interesting. My student Yunchang Ren has shown that if your first guess would be the free group on infinitely many generators, right? Well, that's true most of the time, except if your W is in the commutator subgroup, because then you're forcing the whole thing to be perfect, right? Commutators can't get homomorphisms to anything else. The Xi's end up being commutators. So it's either on F infinity or on some big infinite perfect group, which, and these perfect groups may be of some interest. They're completely defined by this element W. Okay, so that's example 1, example 2, I said 5. Right, example 3, this one is a little bit targeted at the C-star people in the audience. Once again, I should say that I'm sure there's a lot more of these functors, these ways of representing forks than I've thought of. And this one, particular one, I just, it was just sitting there. So K will now be Hilbert spaces. This is this target category. And we're going to take one nice Hilbert space, a little h. And so we have to say what's the image of n, right? These the category C has objects n for the number of these things at the bottom and at the top. So we've got to give an object for n to go to. So phi of n will be simply the direct sum from I equals 1 to n of so n copies of h. Right? I mean, if you don't, they don't have to be Hilbert spaces. If you want them to be just little vector spaces, that's fine too. Even in finite characteristic, this will work. So we've got the direct, and so all we have to do is represent the fork. But what is the fork? Well, it's got to be a mapping which goes from H to H plus H. All right? And if we want it to be in this category, Hilbert space category, it better be an isometry. Okay, so how do we describe an isometry from one Hilbert space to the direct sum with itself? Well, it's just given by a pair of operators, A, B. So this would be psi goes to A psi, B psi, plus B psi. So if we want to have a Hilbert space and therefore have a Hilbert space structure on the direct limit, then we're going to want this to be an isometry. And what's the condition for that to be an isometry? Well, it won't take you long to work out, even if you're not an operator algebraist, that the condition is A star A plus B star B equals the identity. Okay? So that's it. So every time you have a representation of these relations here, A star A plus B star B equals 1, you have an action, unitary action of the Thompson group, unitary representation of the Thompson group, some Hilbert space. Little h could be finite dimensional, nothing wrong with that. It could be one dimensional. So, you know, everyone, when they see this formula, A star A plus B star B, they have a certain gut reaction, and depending on your background, you have a different gut reaction. So probably non-operator algebraists would think first of sine and cosine, right? A is sine theta and B is cosine theta. So in particular, you get unitary representations of the Thompson group for every theta, sine theta, cosine theta. And theta equals 45 degrees should be special, and it is. Turns out that for that value, it's the action on L2 of the unit interval rescaled according to the rate of Nikodym derivative. The other ones is something a bit different. So that's one reaction. The C-star algebraist will say it's just a Course algebra without saying anything else. Well, that's true. That corresponds to the case where this map is a unitary, not just an isometry, because you have this thing the other way around. And so every time you have a representation of Course algebra 2, you get these things. But, you know, a physicist might say, well, no, that's not my first thought. I like fermions. A star A plus A star equals 1. Okay, that's my favorite. And let me tell you, this is quite amusing before I go on. You may ask, well, what is the representation you get from that? Well, you've got to work a little bit, but the answer is, for me, it's pretty surprising. It was a total surprise when I got it. No one will guess, unless you've heard this talk before. So we do this fermion. Starting on a two-dimensional Hilbert space, ends up on an infinite dimensional one. Now, when you don't have any constants like cos theta here, these things are always induced from subgroups. So all I have to tell you is the representation, the subgroup that it's induced from. Okay? The answer is, it's the stabilizer of 1/3. Okay? So the Thompson group acts on the unit interval. Stabilizer fixes a point a third, certain of them fix it, certain of them don't. Stabilizer of 1/3, induce that, get the quasi-regular. That's what you get out of this construction from fermions. All right, Kuntz algebra, blah, 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 so on. So lots of interesting ones. However, I've got two more cases to consider. One of them is, let me do it very quickly because in some sense I did it on Monday. And that's the case where, I just do this here. I start with a Hilbert space H, and I simply change this guy into tensor. So the question there becomes, every time you have an isometry from H to H, tensor H, then you get an action of the Thompson group. Well, there's lots of these things. This was my spin doubling operator in the talk on Monday. The only thing I'd perhaps say with this is that what I proved on Monday, was one of the results that I cited, was that it was in the context of the Thompson group T, and I showed that the rotations in Thompson group T, as the rotation tends to the trivial element, rotation by 1/2 to the n, that sequence of elements tends weakly to 0. well, you can't have fixed points in an action when it's tending weakly to zero. So you get an immediate proof that Thompson T doesn't have Kasdan T. Okay, because you can easily show that there's you make these things where this y tends to something, and so you have almost fixed vectors, but you don't have any fixed vectors. So that was known before by work of Farley, but perhaps never so directly. Right, so finally, the thing that I promised to talk about, which is knot theory. So this would simply be another example. The example, in this case, I'm going to make it a little bit smoother by changing from F to F3. So that just means that instead of using 2 in the definition of the Thompson group, we use 3. Right? Everything else goes through as before, except that the fork, now instead of being a fork with two things like that, it's going to be a fork with 3. So the forests will, instead of being binary, they'll be ternary planar rooted forests. That's a category the same way and so forth. And to get the connection with knot theory, I'm just going to give you in this stuff, I really have to finish by 2, so I'll make a few little lies here, but they can all be corrected in some sense. The idea is very simple. I'm just going to represent it, the fork, by a crossing, okay, and that sort of tells the whole story. If you're a knot theorist, then you take it from there, because what's it going to act on? Well, it's going to act on tangles. So the target category K will be tangles in Conway's sense, which you can linearize or not according to your desire. And you'll notice that there's a pairing on tangles. If you have tangles at T1 and T2, then there's a nice pairing on these tangles where you flip one of them and pair it like that. And I'm going to want to have the structure on my limit, my inductive limit. So I'm going to have to do something about, this. What that corresponds to is that this has to equal this. Well, that's, to the beginner that looks a bit upsetting, but it's, we know how to handle that. You just collect all these distant unknots and throw them away, or you give them a number and linearize things or anything. So somehow you arrange things so that this is true. And then, this fork acting on tangles, if we had a Conway tangle in here, and then we did the fork will act like that. It's obviously going to be a functor. And the only, so the last point that I want to come to is that if you take an element of F, if you take an element F of the Thompson group of now F3, and you do F of that with that, this pairing is this pairing here. What's this 1? That's just a string, right? That's what it is. That's what it looks like. It's just a 1-1 tangle. F11, this is equal to the following. We take the Thompson group element F and we represent it as a pair of ternary trees. Okay, so let's do a simple one. We could keep it nice and simple. This is a pair of ternary trees. I can draw it, and this one comes down there. Okay, there's your pair of ternary trees. Then I'm going to join up these ones in the middle. And I've stuffed it. What's wrong? Oh, I didn't do this one. This is typically what happens. Okay, that's why I sort of always turn one upside down, and then I simply replace these guys by I replace the forks by crossings and maybe tie the top to the bottom like that if I want to. Otherwise I get a 1-1 tangle or a knot, so same sort of thing. So that's the answer. Okay, that's some simple calculation. And if you apply a TQFT to both sides, then this will be a number, and this representation might be unitary and so on, and this would be the coefficients of the unitary representation. And the theorem that obviously has to be proved is, and I actually did prove this, all knots and links arise in this way. So given a knot or link, however complicated it might be, you can always you can sort of turn it into a Thompson group element so that if you do this picture here, then you get your knot back. So in fact, the Thompson group is as good as all of the braid groups at representing knots and links. Missing is, of course, some kind of Markov theorem. All right, well, I'm going to stop there. There's still a lot to say, but I'll stop there now. I have a question. What is this? That obviously defines a universal C-star algebra. Right? What's it called? Well, I asked Wojciechowski and Riefel, and they said, nope, never seen it before. So this guy, which obviously covers the Kunst group, it also covers the free groups. It maps onto the free group algebras by dividing by root 2. It's a big C-star algebra, non-amenable, so on. No one has ever studied it for its own sake. So I'm taking advantage of calling it the Pythagorean C-star algebra. That was my question. Yeah.
I have a question, but it involves a lot of words that I don't understand, so I apologise.
That's all right.
I was wondering whether the category of this category C is it, and I'm going to have to read this out, sorry. The free monoidal category freely generated by an idempotent object. By a single idempotent object.
I don't think so. You mean the category of binary rooted trees?
I mean, I have no idea what that means, but I think that
I
guy's
do
known
know
to
what it
have
means.
Right. I think that guy's known to have some connections with Thompson.
Yeah, sure. Thompson group is that. I should perhaps have emphasised this, that my definition was just like 100,000 other definitions.
Yeah, exactly right.
But I wanted to do it in exactly this way because all those they may be almost they may be exactly equivalent, but no one had ever found these representations, these actions before. So thinking of it as a group of fractions, this category had this huge payoff. Okay, and it wasn't obvious at all. I mean, as I said, the bad thing about it is it totally obscures what I was trying to do. I was thinking of these things as being foliations, piecewise linear foliations of the interval and so on, a very geometric idea about how it would act. And you can do the existence with that, but boy, it's a pain in the neck. I mean, it was pages and pages of pictures and so on and so forth. But this one all came down nicely and extended to other things, just by a slight twist of a lot of other definitions. So yeah. Well, as I said, there's still a lot to say, but I'm out of time.
There's
Cool.
some intuition why the free fermions turn into the stabilizer of the third, just as the simplest sort of way of splitting.
I have none. None. You just do the calculation and you find that it's the stabilizer. It takes a while to do the calculation.
Okay,
actually.
so there's no intuition.
Perhaps I could say that if you look at the work of Gilly Golan and Mark Sapir, if you look at they look at all stabilizers of all points. In fact, they look at finite sets of points, and they write down what they all look like. And for point stabilizers, there's three kinds. There's dyadic rational, rational non-dyadic, and irrational. And they have different groups. Look different, non-isomorphic. And this is that case. Rational non-dyadic.
It's nice somehow.
Oh yeah. I mean, the idea here was that the direct sum of Hilbert spaces, when it gave us our Pythagorean, that was really nice. I mean, that was very, everything's very mellow, and but then when you go into the tensor product, then you're in quantum. It was like first quantization, second quantization. And the second one, you're in trouble because these isometries in the tensor product are much more complicated beasts.
You said, I think, that Thompson T does not have property T.
That's correct.
It's clear that F does not. What about V?
Well, V is, let's see, V doesn't because it contains T, right? Is that the right order of things? Yes.
That's not enough.
That doesn't work, that's not the right order? Okay, well, sorry, it has Hagerov, yeah. I mean, I could get it, I could do it the same way, by the way.
Okay, yeah.
That F doesn't have T is completely trivial because
It's Z.
yeah, but you can also use this to show that the commutative subgroup doesn't have T either, which I think is also known as, well, it has Hagerov, but Hagerov is hereditary. Yeah.
We have a lot of linked invariant coming from many places, quantum groups and so on. If you compose this construction with those invariants, can you get something on the Thompson group? Or?
Well, if you compose, so if you hit the tangles with the TQFT, then these things become just the coefficients of the representation of the Thompson group on that, whatever that Hilbert space is for the TQFT. So, you know, you can say that Thompson group, that you could get the non-T in that way. If you're interested in invariance of links as a, you know, as a thing to do, then, you know, if you hit it with a TQFT, then you're necessarily going to come out with invariance in that TQFT. But I mean, you can imagine playing lots of other games. Just use other pairings. I don't know, put the two together and take the genus or something. That'll probably give you something. But the most obvious one is what I call the Thompson index, right, which is the smallest number of leaves you need to represent it. And it's kind of calculable, unlike the braid index, because each Thompson group, as you add number of leaves, you've got a finite number of elements up to there, so you can just run through them. See if you've got your link, and if you haven't, then its Thompson index is definitely bigger than what you've seen. Yeah.
Have you thought about Thompson's group T? Does it represent sort of all annular links or something?
Well, I've only really thought about it as giving links in this context, just in the same way. But it should, yeah, it should, because that's just a question of changing the target category a little bit.
Right, you just
If you did, I had annular tangles rather than just tangles in a disk. I could probably do that, right? I haven't proved anything about it, but your Thompson groups T, you have to work a little bit. It's a bit confusing to get it as one of these quotients, groups of quotients of a category, but it's okay. You can do it. You have to add, you know, some cyclic groups somewhere. Then for the Thompson group F, you have to add permutations, and then there's some. You work a little bit harder to get representations.
No questions from either audience or the speaker himself? If not, let's thank the speaker again.